G together with combinatorial data of phi multiplied by the logarithmic derivative of the L function at 1 plus the log of the Artin conductor. Just the GONC is what I wrote. This is K north, the normal closure of K. Because K might not be Galois. Yeah, just the normal closure. That's right. Okay, so we're not really relevant to us, but these are numbers that are rational and somehow only depend on combinatorial data. Okay, so this is a beautiful conjecture, and let me write down a sort of immediate corollary of it once you know what modern analytic number theory already knows. And the corollary is that if you look at the faulting height of this abelian variety, I'll write it in absolute value, but in fact faulting height can't get too small, then this grows subpolynomially in the discrete. So it's kind of funny. It's a very beautiful and precise formula, and we're only going to use it in this very sort of perverse, lighthearted way. But without this formula, I'm hard-pressed to give you any bounds whatsoever on this faulting height. So I used to say that I in fact can't give any bounds on it. In fact, I've thought about it. You can probably give some exponential bounds discriminant if you work really hard. But if you want to give a reasonable bound to this quantity, I really can't see how to do it without using precise statements like this. So it's kind of a funny situation. So let me give the proof. Give it inside of the box. Okay, so because these guys only depend on combinatorics, there's finitely many possibilities of them. So if I just show you that all of these terms are small, then that'll show that their sum is small as well. And the proof is the following. So let's see. Well, the Artin conductor is bounded by some power of the discriminant, okay? And log grows subpolynomially. So that's this term here. Proof. We need to bound this from above and this from below. So L1 rho, this is actually the most subtle term in this expression, in absolute value, bounded below by the discriminant, the little of 1. I'm going to get it wrong again. I think it's a Ziegel in this case, right? Or is this Brouwer now? Okay. Brouwer-Ziegel. That's somehow what their main theorem of class groups amounts to, this lower bound. So it's deep. It's been known for a while, but it is somewhat deep. Right. Absolutely. There are certainly several cases you can prove effectively from Stark's theorem, from Stark's work. Oh, I see. Right. Oh, I see. Okay. And so finally you get a bound L1 prime rho, and this is true, that this guy is small is true by the standard convexity bound. This way, the standard convexity bound tells you that L is small near the 1 line, and then you combine it with Cauchy's integral formula, you get it to the derivative as well. Pardon me? Yes. Yes, everywhere here G is absolutely. We're off everything. Yeah, you start observing the degree of the number field. It's a whole different ball game which I know nothing about. The G is always. Okay, but you put these three facts together and you get this from Comet. Known but deep work. Alright, so Comet is not known, and it doesn't seem like it's very close to being known. But there's somehow an average version of it which is known that turns out to be sufficient, which is why we can still end up using this theorem. But I want to save that to the end, and right now let me just show how Comet would apply the Andre-Word conjecture. I want to give you a brief sketch of somehow the ideas behind the proof. So theorem, the Comet conjecture implies Andre-Word. Well, let me say it implies conjecture 1G. That's what I'm pretty good. Okay? So I want to explain how that goes. So it's going to be a few ingredients. One ingredient is going to be this corollary here. Another somehow massive ingredient we're going to use is the theorem of Masser and Wutfeld. The version I'm going to use, I think, was proven in '96, so they worked on it for several years, the refinements of it. And this is going to be a huge powerhouse theorem. They proved it to give a different proof than Poulting's of the Mordell conjecture. Of part of it. Really? Of part of it. Okay? And it says the following. So suppose that A and B, so once again, let's fix G. Always fixed. And suppose A and B are abelian varieties over some number field K of dimension G. And say that somehow I know that they're isogenies. I know there exists some magical isogeny between them. So then it turns out that there is in fact an isogeny between them that's not too big. It's not very big. So then if you let n be the minimal degree of an isogeny between A and B, then n is bounded above by the maximum of the faulting height of A, or I could put B here also, and the degree of the field K over Q to the power of some constant, let me call it C sub G, depending only on G. Okay. So if I give you two abelian varieties that are not arithmetically complex, defined over some low degree numbers. In fact, a low degree isogeny between them. All right? Okay, and it turns out that these two are sufficient to prove conjecture 1G. So let me now give you the proof of 1G from these two guys. And we'll do it as follows. So define a set S to be the set of all abelian varieties A, such that A is principally polarized, the endomorphism ring of A is the full ring of integers of K, and A has CM type K, comma, some phi. Okay? So look at all such abelian varieties. Now in the case of elliptic curves, these form a single Galois orbit. In general, that's very much not true. They can split up into lots of Galois orbits. And even though the size of the Galois orbit we're trying to get at, and that's kind of subtle, the size of S is actually pretty straightforward. So this is up to constants. Let me put it in quotes. I'm not quite sure what the constants are. But the size of this is the size of the class group of K divided by the size of the class group of the totally real subfield of K. And again, using Brouwer's ego, that happens everywhere, this is at least of size discriminant to the 1 coordinate. Okay, so regardless of what's what, if you give me a CM type, then I can give you lots of abelian varieties that are principally polarized of that CM type. So they exist without much fuss. Okay? And let me move over here. So if A and B are in S, then A and B are isogynous. That's true just because they have the same CM type. All abelian varieties of the same CM type are isogynous. And the field by CM theory of definition, let's call it H sub k of A in S, is independent of A. So they're all defined over the same field. That's not too important actually, but it's good to keep in mind. All right, so now all these guys are isogynous, and there's a ton of them. And an abelian variety does not have so many isogenies of a given degree. Only has polynomially many isogenies of degree n. So in fact, what you can do is you can find A, B in S with the minimal degree isogeny, at least, I think it's like the discriminant of k to the 1 over 4g. The power of some number. It doesn't really matter what that number is. So there's two guys that are pretty far apart just by virtue of there being so many of them. So then if we apply Massler-Wustholz, we get that this number, which is at least the size of the minimal degree isogeny, is bounded from above by the max of the faulting height of A and the degree of H sub k to the power of this magical constant T sub g. Okay? And now Colmez tells us that this guy can't be responsible, that this guy grows up polynomially, and so we conclude that this guy is big. As a result, this degree is at least of size the discriminant to the power of 1 over 4g times cg. A little bit. Any power. Yeah. You can actually make it not so bad. So you can actually make this just a quarter if you're a little kid. CG is not so bad now either. It's within a constant of what it should be. It's roughly 2 times g or something. That's much since Massler and Wustholz have improved it. But the problem is, morally speaking, you can't get a good enough constant here. And the point is that you have lots of different CM types. And for different CM types, the Galois orbit's actually of different sizes. So you can at most get the size of the worst orbit. And if you're dealing with the best one, nowhere near good enough. So in principle, this approach, until it can distinguish between CM types, can't really give you good constants, just constants. All right, so that's the end of this proof. So now, maybe I should, well, yeah, let me go over here. All right, so that's how you would do it. Unfortunately, we don't have all of Colmez, but there's work in progress by, I'm going to misspell some names now, so I apologize for that. Andreotti, Goran, I messed up already? Sorry? Oh, there's one. The I is an A. Andreotta. Ah, I see. Thank you. Andreotta, Goran, Howard, and I'm going to screw up even worse now. Metapace, is that right? Tara? I can't even. Let me write MP. MP. I apologize. I'll apologize to him in person next time. All right, but his contribution is not smaller because his name is abbreviated. Kirti, I know his first name. All right, so these four gentlemen have this theorem in the case where you fix K, but you average over all CM types phi. So they have the following theorem, which is that if you sum over phi the faulting height of an abelian variety with CM type K phi, what you get is the sum over all phi of the sum over all rho of somehow what's supposed to go in there, the same thing as you see over there. So they don't quite have this theorem. They're a little bit off. So they get the following theorem, plus at primes dividing twice the log of the discriminant, twice the discriminant, I apologize. Primes dividing twice the discriminant, they're off by rational multiples of log p. Okay? And so they can now show that they aren't off by too much. So each of these numbers is bounded by some absolute constant depending on g. Okay, so they will obviously want to just have this theorem, the average version, but somehow they can't handle some intersection theory at some bad fibers, which is why they're off by these quantities, but they can control how much they're off by. All right? So they have this averaged version, and then it's a fairly old theorem of Bost that if you take any abelian variety A over Q bar of dimension G, then the faulting height of A is actually bounded from below by some constant depending only on G. So let me call it capital A sub G. No, let me call it, I don't know, delta prime sub G. This is a negative constant, by the way, so it's not always positive, but it's still bounded below. Okay. But so as a consequence, you still derive this corollary just the same, because you get an upper bound for the sum. Each term is bounded below, so each term has to be bounded above. All right. Okay, well, that's all I had to say, so maybe I'll just stop here.
Thank you to the organizers, of course, for hosting this nice conference and inviting me to speak, and for all of you for coming after what I gather was a late night for some of you. So, as introduced, I'm going to speak about the dynamical André-Oort conjecture, but I want to start with some classical motivation of this problem, which is, of course, the standard or classical André-Oort conjecture. And I don't particularly want to get into full generality, so what I'm going to talk about is sort of the easiest to state case of the classical André-Oort conjecture. So what does this conjecture say? Well, via the J function, we can consider the complex plane as a parameter space. By the way, is this visible in the back? Yes? Okay. as a parameter space for isomorphism classes of elliptic curves. Okay, and inside of, oh, I'm losing my microphone already. Okay. And inside of this space, we have particular J invariants which correspond to elliptic curves with complex multiplication. So recall that that an elliptic curve has complex multiplication. I think this has already been spoken about, of course, which in the elliptic curve case simply means that the endomorphism ring of the elliptic curve properly contains the integers. And so one sort of natural question that we could ask is, what do, in this parameter space, what do the J invariants of complex multiplication points look like? Okay? And in particular, we might be interested in the geometry of these things. Well, if you're talking about Zariski geometry, this is a one-parameter family, and so the only question you can ask is about whether this collection of points is finite or infinite. Right? So, a few facts for comparison later. Maybe can you come help with this thing? Is it possible? Well, okay, anyways. So a few facts for later. So first of all, there exist infinitely many CMJ invariants. Okay. A second fact, which is a theorem due to Schneider, is that an element of the upper half plane corresponds to a curve with complex multiplication if and only if both tau and its image under the J function are algebraic. Okay? And additionally, thank you. Totally falling here. Sorry.
Just a technical problem.
Oh, we'll see, I guess. Is it possible to sort of... This was predictable, right? Yeah. Okay, anyways, I'll keep talking. So, so if and only if tau and J of tau are both algebraic, and equivalently, tau is a quadratic imaginary. Okay, a few more facts just for analogy. So, secondly, the collection of CMJ invariants over a given number field. So, over a fixed number field K is finite. But I want to point out that this is not a Northcott property. So, in other words, the collection of complex multiplication J invariants is not a set of bounded height, where recall here, by height I mean just the measure of the arithmetic complexity. How long does it take you to write down the minimal polynomial of the number? So they're not a set of bounded height, but nonetheless they satisfy this finiteness property. Okay. So I claimed that I was interested in the geometry of these things, but that in the one parameter setting this isn't so interesting to ask. So let's instead consider a two-parameter space. The easiest one we can build up in this situation is to consider instead C cross C to parameterize pairs of elliptic curves. Okay. In this setting again, sorry, this is a 0. In this setting again, this collection will be Zariski dense in the parameter space, so CM J invariants are Zariski dense in the parameter space. What do I mean by a CMJ invariant in this case? So let's make a definition. In this setting, we call a point, say, AB, special if A is J of tau and B is J of tau prime are both J invariants of CM curves. Okay, so more properly, let's say special points are Zariski dense in this space. Okay, and so then we can ask about the geometry of these things in the following way. Inside of this affine plane, which curves contain infinitely many, or a Zariski dense set of CM, or special points rather. Okay, so question. Which affine curves contain a Zariski dense subset of special points? Well, okay, there's a couple of obvious ones.